All right, this is chapter 7. Chapter 7 will deal with alkenes. Prior to this, we talked about alkanes. And alkanes were carbon single bond molecules. And if I write out this expanded Lewis structure, we recognize this as butane. The ANE says that we have all single bonds. Okay, now this is an expanded Lewis structure. Now we should be able to draw our line angle or skeletal structure, and this butane would be represented by these lines. So we recall that this is a CH3 group, this is a CH2, this is a CH2, this is a CH3. So that refers to that carbon with the two hydrogens. That refers to that carbon with the two hydrogens. This refers to that carbon with the two hydrogens, and this refers to that carbon with the three hydrogens. So when we look at alkenes, alkenes are going to have at least one double bond and the fact that it has one double bond implies two sp2 hybrid carbons. So saying one double bond and two sp2 hybrid carbons is synonymous. That's the exact same thing. So if I looked at a 4-carbon system for an alkene, let's say we have 4 carbons again, okay? And now I'm just going to arbitrarily put a double bond somewhere, and I'm going to fill up the octet with hydrogen. Now, we have not learned how to name these yet, but this is called 2. We will talk about naming in great detail. So, this expanded structure can be represented by, of course, our line angle or skeletal structure. I need 4 carbons, 2, 3, 4, and just for numbering preferences, 2, 3, 4, 1, 2, 3, 4, I will need to put a double bond in between carbon 2 and 3. And this again would give us 2-butene. So the expanded structure and this line angle structure, they are exactly the same molecule. Now, we have to be able to go back and forth between an expanded structure, a condensed structure, and a skeletal or line angle structure, whichever you want to call it. We did this in chapter 1, and this is a review of something that you already know. So if you're given this structure, you recognize that this is a CH2, this is a CH, this is a CH2, this is a CH, and this is a CH2. We recognize it, and we can write out the expanded structure. So I have a 4-carbon system, and I need to draw out 4 carbons. So there's carbon bonded to carbon, bonded to carbon, bonded to carbon. 1, 2, 3, 4, 5. 5-carbon system. So we have 5 carbons, and I can draw out a 5-carbon chain. Now, I can number these 1, 2, 3, 4, 5, like that. And between 1 and 2, I can have a double bond. Between 4 and 5, I can have a double bond, because this will represent carbon 1, 2, 3, 4, and 5. And I need to attach the appropriate number of hydrogen. I would have 2 on carbon 1. I would have 1 on carbon 2. I would have 2 hydrogens on carbon 3. I would have 1 hydrogen on carbon 4, and I would have 2 hydrogens on carbon 5. Our octet can be filled with the remaining hydrogens on each carbon. Now, the molecular orbital theory of sp2 hybridization. This is something that we have already talked about in great detail in chapter 1. So, molecular orbital theory for sp2 hybridization. Okay, this is a review. We learned that for an atom that is sp2 hybridized, we had 3 sp2 molecular orbitals. sp2, and we had one unhybridized p that is perpendicular to the center of the sp2 framework. Okay, so if we look at this figure out of the text, we see that these three sp2 orbitals, they point toward the vertices of an equilateral triangle, and the unhybridized p is indeed perpendicular to the center of the sp2 framework. Okay, from chapter 1, we also recall that the electrons in these 2p orbitals, the overlap of these 2p orbitals, that formed our pi bond. The pi bond, or you can call it the double bond. Okay, so the overlap, the orbital symmetry of these two unhybridized p orbitals, the overlap of the electrons in these orbitals, allowed us to form the pi bond. So in this case, where we have C2H4, this is C2H4, we have overlap between the unhybridized p orbitals and that is going to form your double bond, the double bond that you see here. And you recall that your single bond, your sigma bond here, is formed from the overlap of an sp2 molecular orbital and the atomic peak. You recall that from chapter 1. It's formed from an electron in the sp2 molecular orbital and an electron of the atomic peak. This is your sigma bond here. So in a double bond, you have this sigma and you have one pi. This is information that you already know from chapter 1. Now, to expand on that information, a carbon-carbon single bond is longer than a carbon-carbon double bond. So in order of decreasing bond length, so your carbon-carbon single bond would be longer than your carbon-carbon double bond. And we can see this number in angstroms. Carbon-carbon double bond 1.33 angstroms, where your carbon-carbon single bond is longer, about 1.54. And just to add that your carbon-carbon double bond is also going to be longer than your carbon-carbon triple bond. So as we add these unhybridized p orbitals, our bond lengths within these sp2, and this is of course sp3, excuse me, this is sp, this is sp2, and this is sp3. as we add those unhybridized p orbitals, our bond lengths get shorter. Okay? So, this new concept that we will talk about, elements of unsaturation. Now, you will hear me refer to it as degrees of unsaturation. Some textbooks use hydrogen deficiency index as one term, but in this course you will hear degrees of unsaturation. That is the most common term. Now, to think about what degrees of unsaturation is, recall for a saturated alkane, all single bonds, we had the formula of C to the N, H to the 2N plus 2. Okay? We had that formula. So for however many carbons we had 2N plus 2 hydrogen. So let's say we had a 5 carbon system, 2, 3, 4, 5. So we would have C5H, and then I would do 2 times the number of carbons, which would be 10, and then which would be 5. So it would be 2 times 5 would be 10, and then I would add 2, and that would give me 12. So in this pentane, I should have 12 hydrogen. So I recognize I have 3 here, 2, 2, 2, and 3. So that would be 3 plus 2 is 5, plus 2 is 7, plus 2 is 9, plus 3, and that gives me a total of 12 hydrogen. This is for a saturated alkane. So when we come to degrees of unsaturation, for every degree of unsaturation, we lose 2 hydrogen atoms that would be in a saturated alkane. So I can put in parentheses that would be. So if your system was completely saturated, if we have 1 degree of unsaturation, we would lose 2 hydrogen. If we had 2 degrees of unsaturation, we would lose 4 hydrogen, and so on. So let's look at what constitutes 1 degree of unsaturation. So 1 degree of unsaturation. Okay, so, and this is for alkenes. Alkenes are unsaturated. This is for alkenes. Okay. Alkanes are completely saturated. Alkenes are unsaturated. So what would constitute 1 degree of unsaturation? We can have a case of 1 double bond, that would constitute a degree of unsaturation. 1 ring would constitute a degree of unsaturation. Okay. We can go on adding rules that would constitute 2, 3, 4, and so on. So just look at an example of 2 degrees of unsaturation. 2 degrees of unsaturation, I would have to have a ring and within that ring I would also have to have a double bond. Okay, so you can probably see where I'm going with this. I can have 2 double bonds. And that would constitute 2 degrees of unsaturation. So here, for 1 degree of unsaturation, I can have a double bond like that, and that would constitute 1 degree of unsaturation. I could have a ring structure. I could have cyclohexane, and this will also constitute as 1 degree of unsaturation. Okay, if I look at 2 degrees of unsaturation, so I could have a ring. I could have, let's say, the cyclopentane ring, and then when I add a double bond to it, it becomes cyclopentene. We haven't learned how to name those yet, but we will in this chapter. So this constitutes 2 degrees of unsaturation. I have the ring and I have a double bond within that ring, and I can have a straight chain molecule with 2 double bonds. Those 2 double bonds, 1 double bond is 1 degree, the second double bond makes a 2nd degree. So both of these cases represents 2 degrees of unsaturation. Okay. Now, we could take this further and just by visual inspection, if I had a molecule like this, since I have 3 double bonds in this molecule, this would constitute as 3 degrees of unsaturation. Okay, so relative to the number of rings for now and the number of double bonds, you can somewhat visualize the number of degrees of unsaturation. Now, when we want to get more explicit, if we want to have a molecular formula, let's say given the molecular formula, determine the degrees of unsaturation. Okay, if that was the case, let's say we're given let's say C6H3N Cl and Br. Let's say we have that formula and we want to determine the degree of unsaturation. Well, there is a degree of unsaturation formula. Let's see, degree of unsaturation. And now I'll write that DOU. Well, that is equal to two times the number of carbon atoms plus 2. However many nitrogen atoms you have, you must add that. You can subtract off the number of hydrogen atoms and you can subtract off your halogens, okay? So, and all of that would be divided by 2. So this is the number of nitrogen atoms. This is number of hydrogen. And this is number of halogen. And that's your fluorine, chlorine, bromine, your group 7 elements. Okay? And what you'll begin to see here is that before I go into this formula, your halogens are equivalent to your hydrogens. You know that hydrogen can form one bond with carbon, and you know that your halogens, they can form one bond with carbon. So essentially they are equivalent. Nitrogen will count as half a carbon because it's tetravalent. It can have 3 bonds and 2 long pair of electrons. And oxygen if we have oxygen in our molecular formula, we just want to ignore that. We want to ignore all oxygen atoms. So if we know this formula, this is just good information. This is just good information for you to know. If we know this degree of unsaturation formula here, we can apply it to a molecular formula and determine how many degrees of unsaturation that it actually is. So let's apply that to the example that we have. And We know it's going to be divided by 2. So we have 2 times the number of carbon atoms. In this example, we have 6. Okay, and then we're going to add 2 to that. So that covers a saturated alkane. That's where we get that formula from. Okay, now since nitrogen is counted as half a carbon, we will only add 1 to that formula. So we have 1 nitrogen molecule. So we will add 1. And we want to subtract off the number of hydrogen, which we have 3 here. And we want to subtract off the halogen. Br is a halogen and chlorine is a halogen. So we have 2 of those. So we want to subtract off 2. And then we want to simplify this. So we would have 12 plus 2 plus 1 minus 5. And that's going to be all divided by 2. So 12 plus 2 gives us 14. Plus 1 gives us 15. Minus 5 would be 15 minus 5 would be 10. And then we divide that by 2. And that's equal to 5. So the solution to this problem is we have 5 degrees of unsaturation. Okay. Now, what if we have another example? And let's just open a new whiteboard to practice these other examples. Let's just say we have another molecular formula. Molecular formula. Okay, say we have this molecular formula, C9H N O 4. Let's say we have that molecular formula and we want to determine the degree of unsaturation. So degree of unsaturation our formula is going to be 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of hydrogens, write that, and minus the number of halogen, all divided by 2. Okay, so what that would equal to we have 2 times 9 plus 1 nitrogen. We want to subtract 9 hydrogen, and we have 0 halogen, and we want to disregard the oxygens altogether, okay? And then we want to divide that number by 2. So what we wind up with is 18 plus 1 So that would be 2 times 9 plus 2 here, plus 2, plus 1 nitrogen, minus 9, minus 0. Okay. Now, so what we will have is 18 plus 2 plus 1 minus 9 minus 0. And that's all divided by 2. So this would give me 21 minus 9. So that would give me 12. And then I need to divide that number by 2. And that would give me 6. So we have 6 degrees of unsaturation for C9H9NO4. Okay, so we need to keep in mind that we have 2 times the carbons plus 2 plus the number of nitrogen, and we subtract off the number of hydrogen and subtract off the number of halogen, and we simply ignore all oxygen. Okay. All right, let's do another example. So if we have the molecular formula what if we have, let's say C9H20. So if we have C9H20, our degree of unsaturation is equal to write out our formula. It would be 2 times the number of carbons plus 2 plus the number of nitrogen minus the number of hydrogen minus the number of halogen. All of that would be divided by 2. So that's equal to 2 times 9 plus 2. And we don't have any nitrogen. We have 20 oxygen, and we have no halogen. So you can either write out that step of plus 0 or minus 0 if we don't have those atoms, or you can simply leave it off. So what we wind up with is 18 plus 2 minus 20, all divided by 2. And that's going to be 20 minus 20 divided by 2, which is 0. So we have 0 degrees of unsaturation. And another way of saying that is that this molecule is saturated. So there are no elements of unsaturation in this molecule. This molecule is completely saturated. All right. Now, what if we have the structure, let's say determine the degree of unsaturation given the following structure. Okay? So, let's say we have this structure. Let's say we have nitrogen in the center. And we have two double bonds. And we have a chlorine. Like so. Now, we could look at this and we could determine there are 3 degrees of unsaturation. The fact that we have 1 ring and 2 double bonds. That's one way we could look at it. We could say 1 ring plus 2 double bonds equals 3 degrees of unsaturation. That's one way we can approach this problem. The other way is that we can write out the complete 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. We could write out the complete molecular formula and use the degree of unsaturation formula. So let's count up how many carbon we have. We have 1, 2, 3, 4. We have 4 carbons, so that would be C4. We have how many nitrogens? 1, 2, 3. So that would be H3. And what else do we have left? We have this chlorine. So this is our molecular formula. And this would be a good check to see did we come up with the right hypothesis of 3 degrees of unsaturation. So I can say degree of unsaturation is equal to, the more you write this formula out, the more familiar you will be with it, and it will become second nature. So we have 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of hydrogens minus the number of halogen. All of that is going to be divided by 2. So what that gives us is we can simply plug in that formula. We have 2 times 4 carbons plus 2 So that's essentially telling us the number of hydrogen that we should have, okay? We don't have any nitrogen, so I don't have any term for that. I can subtract off the 3 hydrogen that I have and subtract off the 1 halogen and divide all of that by 2. Okay? Now, we simplify our problem, so that gives us what? 8 plus 2. That's equal to 10 minus 3. That's 7 minus 1, and that gives us 6. Divided by 2. 6 divided by 2 gives us 3. So that's exactly what we found here. So we have 3 degrees of unsaturation. Okay? Now, let's look at another molecule. Let's look at, let's see. Let's look at this molecule. So right offhand, we should be able to look at this molecule and we should say, okay, we have 2 double bonds here, or not say 2 double bonds, we have a double bond and a triple bond. So those 2 multiple bonds, they each count for 1 degree of unsaturation, and I have a double bond here. And that counts as 1 degree of unsaturation. So I have 1 degree here, 1 degree here, 1 degree here. 1 plus 1 plus 1. So we should wind up with 3 degrees of unsaturation. Okay, if we have 3 degrees of unsaturation, we can verify this by actually writing out what the molecular formula is. So we know this is a CH3, this is a CH2, this is a C, this is a CH2, this is a CH, and this is a CH2. So we have 1, 2, 3, 4, 5, 6, 7. We have 7 carbons. We have 3, 5, 6, 7, 8, 9, 10. We have 10 hydrogens, if I counted that correctly. So this is our molecular formula. And we can apply the degree of unsaturation formula. And we can say that it's going to be simple here because we only have carbon and hydrogen. So 2 times the number of carbon plus 2 minus the number, plus the number of nitrogen minus the number of hydrogen minus the number of halogen. And that's all going to be divided by 2. So what we wind up with is 2 times 7 plus 2 minus 10. So we would have 14 plus 2, which would be 16, minus 10. 16 minus 10 gives us 6, and that divided by 2 gives us 3. So we have verified using the degree of unsaturation formula here what we knew by looking at the multiple bonds in the molecule. You should get the same number upon visual inspection, counting the double and triple bonds and rings, and doing the molecular formula for degrees of unsaturation. Okay, now for practice. There is a lot of practice in the textbook that I will be assigning, but for practice, let's say we have this structure. Let's say we have this structure. This structure has a special name. This structure has a special name for students in chemistry, biology, and medicine. This structure has a special name. Okay, so determine the degree or degrees of unsaturation for this molecule. So, I want this done two ways. One, visual inspection, and that means what? Counting rings and double and triple bonds. Number two, using the molecular formula. So you have to look at this molecule and you have to apply what you learned in chapter 1 to determine I have a certain number of carbon atoms, I have a certain number of hydrogen atoms, and I have a certain number of oxygen atoms. You should be able to look at this molecular structure and determine its molecular formula. And using the molecular formula, you can determine the degree of unsaturation. If you're not able to determine the molecular formula, you will have a problem using the degree of unsaturation formula to determine the sites of unsaturation. All right, we will stop here for now and continue with the second part of chapter 7 next time.